Hey guys, I'm also new faculty like Adner. I'm opening a lab in URI. I arrived in July, and I might be the reason we're speaking English today. And I don't need to speak Hebrew. Oh, thanks. Good. So let's keep speaking. Okay, so my lab is generally focused on the.
Which faculty are you affiliated with?
I'm affiliated with medicine, but I spend most of my lab, most of my time here in electrical engineering. I also live on campus, so for now it's way easier to commute here most of the days. I originally studied theoretical physics, Higgs boson, and then I moved to neuroscience and artificial intelligence. So if you're looking for a changing career and moving to more interesting sciences, it's a different conversation, but most happy to. So the lab is centered around the ideas of neuroscience, as Avner presented, and machine learning or artificial intelligence. So we develop tools to understand the brain, and we exploit ideas from neuroscience to make machines better and more biologically plausible. So the synergy between these two important fields is really where the lab, where the ideas are taken. And specifically, the focus is to develop theoretical and computational insights into how neural representation works. So neural representation are the inner mechanisms of both the brain and neural networks, and we try to understand why and how they work. So in the lab, we do three things. We develop theory of different kinds, from statistical physics, dynamical systems, and so on. We have multiple collaborations with neuroscience labs. We analyze a lot of neuroscience data, and we develop machine learning algorithms. One example of this trajectory is the following. We're interested in animal behavior, but more specifically, we're interested in the circuit mechanisms in the brain that generate these behaviors. Like Avner, there was no better setup of what I'm saying than other stuff. And why we do this in animals is because of what Avner was saying, that we can record neurons, we can modify these neurons and target with very high precision the circuit. We know the connectivity, and we can interface with the brain in a perturbative causal way. So we can really understand how the circuit generates representations and how these representations in turn generate animal behavior. Let me see if I can. Okay, here. So the focus of the lab is really in a way this middle ground between like the circuit mechanisms and the generation, the output of behavior decisions and other tasks. And this middle ground is really also where neural networks come in. So while this is the biological angle of the lab, there is also like a lot of artificial neural networks development and the same understanding of how neural representations arise, how they're shaped by learning and task demands, and how we can make them better. So the lab generally is focused on neural networks in biological and artificial systems. I think because this is a autonomous, right, and robotic kind of program, the two problems on which we're focusing right now that are most aligned with these are the following, and they belong to the navigation problem, which is also Avner was touching about. Yesterday, I couldn't download the movie. I'm sorry, guys, the internet was too slow. But imagine navigating a video game or any room, or going, as Avner was saying, from one place to another. And this problem is targeted in completely different ways if we look into a robot or if we look into the brain. So let's do the exercise 1 second to think of how a robot would implement this and how our brain would implement this. Okay. So one project in the lab is to look at SLAM. I think SLAM stands for simultaneous localization and mapping, as all of you know, I believe. And one of the projects in the lab is to think of SLAM in collaboration with a friend of Mobileye, is to understand how SLAM is implemented, and specifically replace one component of SLAM, that is the keyframe selection, that selects the frames that are maintained in the memory of the algorithm for the purpose of localization and mapping, and transform this component into something that is slightly closer to how the brain does it with neural network architecture. So we're looking into replacing the keyframe selection component with a transformer neural network. This is something that is nothing new in some ways, but it hasn't been done in the way that we are trying here before. So if you are interested in, if you know SLAM very well and you're interested in this type of project, please come let us know. And this is kind of the way I look at these projects, right? Here we're taking an algorithm that is how it's implemented in a robot or in the mobile algorithm and try to see if we can solve it with neural network with machine learning tools. But there is a counterpart to this, that is we can look at the brain and see if we can turn it into numbers. Okay, and this is roughly the other side of it, okay, where we consider an agent that is navigating a simplified environment, in this case, a simulated agent, not a robot, that is navigating, say, a square room. Okay? And the agent is sensing some information from the walls. And we ask when and how the agent would extract a map of the environment, a representation of the environment that is navigating. To understand this, we train the network, in this case, a recurrent neural network, where we feed the actions and observations to the agent, and we ask the agent to predict the upcoming sensory observations. So the agent is turning and is trying to predict what it's going to see upon turning. And what we found is that by means of these predictive task demands, the agent does extract a map of the environment. Here, the environment is pictured as a square, and each tile in the environment is of a specific color, and there is a single trajectory of the agent. And what you see here is instead a representation of the internal activations of the network. And each of these points is a specific activation set of the network that corresponds to when the agent was in that specific time. So the color corresponds to where the agent is, but this is its brain in a way, synthetic brain. And what I think you can see is that the representation of the neural network does reflect partly the two-dimensional arrangement of the environment of the room, but it is more complicated. There is way more information there because the sensory observation, the action, and the environmental map are all packed within one representation. What we're trying to do now is to essentially ask more questions on top of this setup. What happens if we, for example, add a reward to this environment? And we train the agent not only to predict future observation, but also to maximize rewards. How will the network then co-encode the observation, action, special encoding, and rewards? How can all of these different types of information be co-encoded in the network representation? For example, one thing that we see is that if you add a reward in this spot, we see a deformation of the manifolds that tries to stretch essentially the encoding of the activations of the network to make it more precise for spots around it. And we look at all sorts of phenomena that deal with navigation and encoding of rewards and agency more generally. So these are two of the several directions that we're taking. On SLAM, on navigation with different machine learning network. And if you're interested in more of this type of direction at the intersection of neuroscience and artificial intelligence, please come.